everyone, the purpose of this video is to look at titration curves, which we looked at for weak acids and weak bases specifically. So either a weak acid with a strong base or a weak base with a strong acid. And the importance of the half equivalence point and how the half equivalence point can connect to pKa and pKb. All right, so let's consider titration. And I have here a titration between a weak base and a strong acid. So let's say I start with my weak base down here and my strong acid up here. NH3, remember, is one of those exceptions. So when we write the equation for the reaction of NH3, well, ammonia is actually a synthesis reaction. So it's unlike most acid-base reactions that produce a salt and water, ammonia does a synthesis reaction. Okay, so at the equivalence point, if I'm at the equivalence point for my weak acid and strong base here, well, at the equivalence point, all of my NH3 will have reacted with all of my HCl, and I'll have only NH4Cl in my flask, is the idea. So the exact equivalence point is when these have reacted completely, neither is in excess, you have only product present. Neither of your reactants, because both of them have completely reacted, and neither of them is there in excess. All right, so let's think about the half equivalence point. Let's say I have in my flask, let's say I start with 1 mole of NH3, and let's say that here I start adding my HCl drop by drop, and let's think about the point when I've added half of a mole of HCl. Well, my coefficients here are 1, 1, and 1, which is really convenient because when I've added half of a mole of HCl, that means that half of a mole of NH3 has reacted. So when I have added half a mole of HCl, I should have half of a mole of NH3 left. Awesome. So what does that mean? At the half equivalence point, the concentration of my acid is equal to the concentration of my base because I'm halfway to the point of both my acid and base reacting completely to get me to the product. Okay, and remember this happens even when you have a weak base or weak acid, you still have both of your reactants react completely. It's just that it takes a little bit longer for the NH3 to react than if it were a strong base, something like NaOH, where all of these would immediately disassociate and the OHs would be super available to react. So even though it's a weak base, all of the NH3 will react with all of the HCl at the equivalence point. At half of the equivalence point, the concentration of acid will be equal to the concentration of base, like we showed here. Great, so why does all that matter? Well, let's take a look at an equation we saw in option D. We looked at this as a class. We also saw it a little bit when we did buffers. So we know that pH is equal to pKa plus the log of my base over my acid. Great, why does this matter so much? Well, and we have the same thing here. The inverse is also true. pOH, or not the inverse, I should say, but it's also true. The pOH equals pKb plus log of acid over base for weak base. Awesome. Well, how does this apply? Let's take a look at my curves here. These are all the curves that I could have, either a strong acid, strong bases. We really focused on when you have one of them being weak, either weak base or weak acid. And that's true in these cases. Notice weak acid, weak base, you don't get a nice equivalence point. And these two different types of graphs come from either starting with a base, and so we start with basic pHs, or starting with an acid, so we start with acid pHs. We see that the equivalence point is going to be either lower than 7 if I have a strong acid, higher than 7 if I have a strong base, or around 7 if both of them are strong, or if both of them are weak. All right, So there's our equivalence point. Our half equivalence point is going to be halfway to the start of your titration and the equivalence point. So somewhere here or here or here, halfway in between the start and when we start reaching the equivalence point. All right, why is that half equivalence point so important? Well, it's going back to what we were just saying before. At the half equivalence point, the concentration of base is equal to the concentration of acid. Same thing here, the concentration of acid is equal to the concentration of base. So at the half equivalence point, I'm realizing my arrows are getting confusing, the concentration of acid and base should be exactly equal. Well, what's log of 1, right? If this is equal to this, then that would just be equal to 1. What's log of 1? Log of 1 is actually 0. So that means that if the concentration of acid is equal to the concentration of base, which happens at the half equivalence point, well, then this term becomes 0 and pH is equal to the pKa. And that's going to be true regardless of what situation you're looking at. If you have a weak acid or weak base, we can also look at this equation. The pOH will be equal to the pKb at the half equivalence point. So at half equivalence, regardless of what situation you have, acids, bases, whatever, at half equivalence, pH is equal to pKa, pOH is equal to pKb. So for a problem like this one that you saw in the topic 18 practice, sketch a graph of pH against volume of hydrochloric acid added to ammonia. Ammonia is a base. Hydrochloric acid is, of course, a strong acid. So the acids being added to the base, we start with basic pHs, and we have a strong acid. So my equivalence point better be lower than 7, and we'll have something like this. How would I estimate the pKa of the ammonium ion? Well, the half equivalence point, that's going to be pH is equal to pKa here, pOH is equal to pKb here, and so, I don't know, somewhere around, let's see what the IB considered a reasonable estimate. They didn't really give us a number here, right? They actually just annotated the graph. So they were looking for correct shape of the graph, and they were looking for identifying that half equivalence point. All right, I hope that helped. Thank you for watching. Have a good day. Good luck with your studying.